Okay, so the course objectives and outlines is in the modal, and we talked about a number of items on this, particularly the course weighting and stuff like that, and the exams, midterm and final exams. But also, you will see a list of topics that I plan to cover as much as possible. Okay, so pretty soon, today, if not next lecture, certainly, to start looking at introduction to vectors and tensors, and then start developing the governing equations of motion, and then solutions of a variety of problems leading up to turbulence and stability and stuff like that. And at the end of this document, you will see a fairly extensive bibliography. Okay? So, as I said, this is a graduate course, and you should kind of check out a few of these books from the library to use as additional material and then circulate it among yourself. Most of the material I'll be taking from the first three books, Bird, Stewart, and Lightfoot being the primary resource, and then the book by Leal on advanced transport phenomena, and then the book by Kundu on fluid mechanics. Maybe a bit from Dean as well, analysis of transport phenomena. Okay, so it's there on the web, so you can download it. And I've also posted the audio-video lecture from the first lecture, which you can also download if you want to download onto your portable device by going to this link where it says downloading. And when you go there, it will just give you, in fact, all the files that I have related to this course will be accessible for download. Okay, so whether it's the lectures, assignments, solutions, etc. And each lecture is about 85 meg or so. The audio-video portion of the lecture will be about 85 meg. So if you do it on campus, it might download reasonably fast. But if you do it outside at home, it may be a bit slow. Any questions, comments, feedbacks for me about this course so far? The pace? Okay. On Tuesday next week, I will be away. So my graduate student, Tom Scher, he will come and give the lecture, but it's not going to be a lecture on the fluid mechanics or transport phenomena, but introducing you to the computing environment that is available in LSU. Okay, so he will introduce you to MATLAB, Maple. How many of you have used MATLAB before? Maple a little bit, and Maple is a symbolic program. Mathematica is very much like that, and MATLAB is numerical environment, but it has a symbolic toolbox as well. And you might find these useful while doing assignments and taking simple derivatives and stuff like that. Maple or MATLAB symbolic toolbox will make your life a lot easier. There was one incident, I think 2 years ago, I gave an assignment and one student did entirely in, I think, Mathematica. He was familiar with Mathematica. So you could do that. Okay, so because it's basically taking derivatives, integrals, and these toolboxes can do it for you without any algebraic error. If you do it by hand, you will get into those problems. So Tuesday he will take the class, and then Thursday I'll be back. Okay. Of course, I have put this notes, and some of you have, I guess most of you have downloaded it. But let's just close that and talk about what you have learned from the last lecture. If you have to point out one or two things that sticks in your mind from the last lecture, what would that be? Nothing? That's a pretty sad state. Pardon me? 4 years law. Okay. That sticks to in your mind. That's the front cover of the book also, I think, the current edition of the book. So those constitutive models. Okay, what do they do? This is where the 7 hour helps. 1 hour lecture followed by a review would help. They relate transport that is occurring at the molecular level to the continuum level. So they allow you to get rid of the molecular level of worrying and then say, I can describe in an empirical way the relationship between fluxes and gradients, whether it is momentum flux, heat flux, or mass flux, in terms of the driving force, which is the gradient in space. Okay? Anybody else remembers anything else from that course, from that lecture? That is very important. It's the basis of the similarity, the uniformity in transport phenomena. All are fundamentally derived from molecular processes.
A relative magnitude
Of
size motion.
the scales, we talked about scales. Okay, the phenomena occurring over a wide range of scales, and we are going to be looking at something called the continuum scale. Okay, so the continuum postulate is an important concept. Okay, and we said that we are going to define the idea of continuum postulate is that we can treat any fluid as a continuous material, so that we can talk of density, velocity, pressure at a point. Okay, but when I say a point, the point is not a mathematical limit going to zero, even though that's how we define the mathematical derivative. Okay, as a limit delta x going to zero, delta f over delta x is df over dx. That's how we define a derivative. But we have to keep in mind, in this context of a continuum postulate, that that limit must remain large compared to what? The mean free path. Okay, there is a distance the molecules travel before they bump into each other. That's the average free distance that they can travel. Okay, and so that is a very key idea, because the whole thing that we are going to look at is on continuum scale. So it's called continuum. It's a branch of continuum mechanics. Fluid mechanics is. So continuum postulate is valid if this ratio, the ratio of the mean free path, lambda, to the length scale in the process equivalent, if that is much, much smaller than 1, then continuum postulate is valid. So what do I mean by that? If I have, for example, a tiny pore in a catalyst pellet, okay? So I have a catalyst pellet, but it has a lot of tiny pores, and through these pores, the molecule has to diffuse into it to attach to the surface and catalytically react, and the product comes out. So if the pore size is comparable, the same length scale as the mean free path, then the continuum mechanics will fail. Okay? So in those situations, Knudsen number is close to 1, and we have something called Knudsen diffusion. It's not Fickian diffusion anymore. Diffusion is not governed by Fick's law, but it is governed by Knudsen diffusion. Okay, and there are separate models for that. But as long as we are away from that situation, that our equipment size is much larger compared to the mean free path, we are okay to assume that the continuum postulate is valid. Okay. So we talked about the molecular nature of the fluid. We talked about gravity as being a long-range force. Maybe I did not emphasize that it is a long-range force, but we identified gravity, electromagnetic, and strong and weak nuclear forces as 4 fundamental forces. And gravity acts over very long distances between planets and galaxies and stuff like that. Whereas the molecular interactions, the electron-cloud interaction, is called a short-range force because they act only very close to each other. Okay, so they are called, sometimes they are called surface forces, whereas long-range forces are called volume forces. Why? Because gravity acts over the entire volume. Today, in fact, we will look at buoyancy, and we will see that it acts over the entire volume, whereas pressure, shear, these are all having origin in the molecular interaction, are short-range forces, and they are called surface forces. They act as if they're acting on a surface. Okay, And then we saw about non-Newtonian behavior of certain fluids that don't obey. So those three equations that we saw are not universal in any sense. Only certain types of fluids will obey them. Luckily for us, air and water, most two abundant fluids on the planet, obey the Newtonian law of viscosity. But there are materials that don't. Okay. And we started talking about this continuum mechanics. Continuum mechanics is study of forces acting on continuous deformable material. Okay. So there are two branches to it, solid mechanics and fluid mechanics. And we are going to focus on fluid mechanics in this course, but the principles are basically applying Newton's law of motion in either case. And then studying when you apply force, what happens to that material, whether it's a solid or a fluid. And in solid, we saw already that it can be elastic, meaning when I apply a force, it deforms, but when you remove the force, it goes back to its position. It's as if it has memory of the original position. Whereas plastic material are those that will deform slowly. So if you keep applying the force for a while, the material will deform and change shape and will not be able to go back to the original shape. Did anybody see the movie by J.A. Taylor, the whole 30 minutes of it? No? Okay. You should. There is one short clip about glaciers. So nobody saw that movie? I thought two people did. Yeah, two people saw it. I can monitor who sees it. So did you see that glacier movement?
Is movie moment?
Right, right. So he has a film where he goes to, I think it's probably in Canada, I'm not sure. There's a huge glacier. Glaciers are basically large ice masses. And we think of ice as a solid material, right? But even glaciers can move as a fluid over a longer period of time. So what he does is, if you see the film, there is a glacier, and he will put a lot of red marks, pegs, that he just puts it on the glacier. It goes away. 2 years later, he comes back to see what happened to those. And what you will find is that it is like this. They've all moved. This peg has moved this much, this peg has moved this much, etc. We will study later on in this course that when you look at the flow in a pipe, the profile, the velocity profile is exactly like this, a parabola. So you can think of ice as a fluid over long time scale. In fact, that is the point that the last clip that we saw in the last lecture was driving. If you take silly putty and hit it on the floor, it bounces like a solid, like an elastic material. But you leave it there, it just flows like a fluid. So there are some material that cannot be classified strictly either as solid or as fluid. They behave like a solid on short time scale compared to the relaxation time of the material, and they will act like a fluid, flow like a fluid over a long time scale. So it is as if the glacier has a very, very high viscosity. Okay, that's why it is acting like a solid. But over a long time scale, it will move like a fluid with very similar flow characteristics like a fluid. Okay. Then we saw the non-Newtonian fluid mechanics, those that do not obey the linear relationship between the stress and the rate of strain. These are important concepts. I will have a quiz pretty soon where I will ask you to explain these things in brief term and identify various types of concepts that we have seen. Rheology is a subject in its own right, and that deals with both solids and fluids. How do we relate this constitutive relationship? When Newton's law is not valid, what are the other laws? How do I go and study them? How do I measure them? How do I build models for them? And that is the topic of rheology, mostly with polymers. A lot of food processing operations, tomato ketchup, toothpaste. These things are all having a very complicated relationship between the stress and the rate of strain. They will all be classified as non-Newtonian. And rheology is the study of what that relationship is between the stress and the rate of strain for a variety of these materials. So we already talked about these constitutive models. They are empirical in nature, and I'm going to go through them quickly to identify what is the quantity that we are defining. Whenever, this is an important idea, whenever we change scales from molecular scale to continuum scale or from continuum scale to a higher scale, we are averaging, we are collecting 1,000 molecules and say there is each molecule itself has individual velocity, but we are saying what is the average velocity. When I say the average velocity of this collection of 1,000 molecules is 1 meter per second, I don't have the ability to tell what is the velocity of each individual molecule because I have averaged them out. So in a sense, what I'm saying is this idea of if you give me a function, I can define what is the average for that function. How would I find the average for that function? This is f of x versus x between a and b. And I want you to find the average. The way we would define that average is, I'll find what is the area under the curve, and I will find an equivalent rectangle that has the same area, and I will call this as my average. So that average height times the width b minus a should be equal to the integral of f of x dx from a to b. So that is one way of defining what that average is. Okay? But if I tell you the function and then say find me an average, you should be able to do it by doing the integration. But if I tell you this is the average and say find me a function, there is no unique function. Many different functions could have that average. So we have lost that information in going from a differential scale to an integral scale. We have lost when we do the integration, when we do the averaging, we lose the information. Okay, and that information is what provided empirically. These are all laws observed empirically by various researchers, Fick, Fourier, and Newton. Okay, it's an empirical observation saying that this works. The linear relationship works. So in this one, what we are doing is we are measuring what the mass flux is. And the mass flux is going to be defined as kilogram per meter squared second. It is defined as a flux. Okay. So what we are doing, the thought experiment that we are doing is, if I have a cube like this, I'm going to take this area. And so I know the area meter squared. I'm going to find out how many kilograms passes through that per second. Okay. That is what we call the flux. And that flux, we know empirically, is proportional to the gradient. This is a three-dimensional equation. Okay. So this is actually a vector form of the equation. When I write it in bold case, that J actually stands for Jx, Jy, Jz. So there are three components of that flux vector in each one of the three directions. And does anybody know what this term is? Gradient of CA? It is the gradient of that function. Gradient is also a vector. Okay. So the gradient of CA will be defined as dCA dx, dCA dy, dCA dz. Now a lot of these vectors and tensors, you can look at the book by Kundu or the book by Burstner and Lightfoot in the appendix. You'll find these things reviewed. Okay. So when I write an equation like this, I am implying that there are three equations, three components of the equation. So when I expand them, it's going to be something like Jx equals minus dAV times dCA dx. Similarly for y and similarly for z. Okay. So that is a vector equation, and the gradient, what will be the units for the gradient? Concentration could be in terms of kilograms per meter cube. Okay, so Ca in terms of kilograms per meter cube, and the gradient operator has d dx. Okay, so the del operator has the units of 1 over meter. Okay, so what will be the units of gradient of Ca? Kilogram per meter to the power 4. Okay, so this proportionality is made into an equation by introducing this diffusivity as a property. So it is an equation that defines what diffusivity is. And in an experiment, we need to find clever ways of measuring the flux, measuring the gradient, so that we can back calculate what diffusivity is. And there are then, these are tabulated, so it's available for us. Okay, so what should be the unit for this diffusivity? you should find the unit for this diffusivity in such a way that that equation is dimensionally consistent. What do I mean by that? The units on the left hand side must be equal to the units on the right hand side. So when you do that, what will you get? On the left hand side you have kg per meter square second. This is the left hand side. On the right hand side you will have kg per meter to the power 4, right? So kg and kg will cancel out, meter square, one of them will cancel out, so D should have the units of meter square per second. So D should have the units of meter square per second. You should be able to do the same thing for the remaining two equations. Okay? Find out how the flux is defined, find out how the gradient is defined, and that introduces the property called thermal conductivity in the case of heat transfer. So what should be the units for the thermal conductivity? So I'll leave that as an assignment for you guys to do. Okay. Now, in the case of mass transfer and heat transfer, we have only a vector quantity to deal with because this Q is also a vector consisting of Qx, Qy, and Qz. Okay, that is the heat flux across a particular surface. You identify a surface, normal to that surface, you have a flux. Okay, and the gradient is pointing in the same direction, gradient of temperature. So this simply says that the heat goes in the direction of the decreasing temperature gradient, the steepest temperature change. Okay? But when it comes to fluid mechanics, this constitutive equation is a bit more difficult, as we saw already in the last class. When I have a motion in the horizontal direction, that transfers the momentum in the perpendicular direction by molecular interaction. So that's why we have this tau has two subscripts, x, y. Okay, so what this means is if I have, once again, that cube, the control volume, this being x direction, y direction, and z direction. Okay, so I have a surface I would call the x surface. By that I mean a surface that has normal in the x direction. So this will be labeled as the x surface. Okay, and then I have on that surface I can have a force that is acting in any one of the three directions. Okay, so I could have a force that is acting in this direction, a force that is acting in this direction, or a force that is acting there on that one surface. So how will I label them? I will label this, for example, as tau xx, meaning it is acting on the x surface in the x direction. Okay, are you with me? So how would I label this one? On the x surface in the y direction. Okay, tau xy. So this one would be tau xz. This is why we see for the first time that the stress is not a vector. Flux, heat flux, mass flux are vectors, but the momentum flux is a tensor. Meaning I have identified one surface. On that surface I have three components. I have two more surfaces to worry about. A surface that is having a normal in the y direction, this surface, and a surface that has a normal in the z direction. So on each one of these surfaces I have three more forces. That's why I need two subscripts. A vector, I need only one subscript. There are three components. A tensor has two subscripts, has 9 components. So the stress is a tensor from that point of view. But the simplest form that you would have seen in undergraduate fluid mechanics is that component is tau xy, for example, is equal to mu times du dy. U is the x component velocity, y is the gradient of the y component. Okay, and you can divide this and multiply it by the density. So I guess I got this wrong. It should be mu over rho. Okay, and then this rho times u is essentially your momentum. It's mass times the velocity. But rho is a density per unit mass per unit volume. So rho u is actually momentum per unit volume. Okay, so that's how we give it an interpretation of a momentum flux. Okay, rho u is the momentum flux, and so this is the real property that we need to introduce. Even though viscosity is the one that we introduce in the constitutive equation, mu is called the kinematic viscosity, which is mu divided by rho, and it will also have the same units, meter squared per second. Okay. Diffusivity has the same units. Thermal conductivity, for example, will not have the same units, but thermal diffusivity will have the same units. That is, alpha equals K over rho Cp. That's called the thermal diffusivity, and that should have the same units, meter per second. So this analogy goes beyond just very superfluous similarities in the molecular interaction. Okay, the properties, when defined properly, like momentum diffusivity, mass diffusivity, heat diffusivity, or thermal diffusivity, they will all have the same units. When you are looking at them as fluxes, so in this case, if you look at du dy, that is not a momentum flux, but d times rho u dy is a momentum flux. In the same way, let me ask you, this is not in the note, so maybe it gives you time to think about. What should I do to this equation to make it like gradient of a energy flux? Temperature is not energy, right? The answer is, in some sense, I have to make sure that you understand the question. The answer is staring at you. The question is, what should you do to this equation to make it look like heat flux is proportional to gradient of heat, not gradient of temperature? Like the mass flux was proportional to gradient of mass concentration. So the unit for diffusivity automatically came out to be meter squared per second. For viscosity, it didn't. Viscosity has the units of kg per meter second. But when you put it as momentum flux, rho u, and in order to do that, you multiply and divide by rho. If you're not following me, please do stop. Okay. So this is the original form. Tau equals mu times du dy. This is Newton's law of viscosity, empirical, given to you. You can find out what is the units of mu, the viscosity. It will be kilogram per meter second. But when I manipulate it by multiplying and dividing by rho, so that I can look at this rho u as a momentum, the interpretation for mass times velocity per unit volume is momentum flux. Okay? So when I interpret it like momentum, then this quantity, which is mu divided by rho, truly becomes a momentum diffusivity. Okay? It's called momentum diffusivity, it's called kinematic viscosity, it has the units of meter squared per second. So what did I do here? I expressed the term in this as a momentum term per unit volume. So what should I do to the heat equation to get the same form? The heat equation is only... Good. Repeat it again. Cp. It has to be multiplied by rho Cp. Rho Cpt. And you also have to divide by rho Cp to cancel it out. Okay? Now, if you figure out the units for rho Cpt, that will be in terms of joules per unit volume. Okay, so now we are talking about energy flux, gradient of the energy flux being that alpha that you will define such that K over rho Cp will have the same units, meter square per second. This analogy is really very deep. Later on in the course, we will see that if I can study, for example, the rate of heat transfer from a surface, and if I measure that, I can use that to predict the rate of mass transfer, because the analogy is so close. Mathematically, they are the same equations. That means as long as I take care of physical property difference, I should be able to transfer the information from momentum transfer to heat transfer to mass transfer. In undergraduate course, you would have seen something called analogies. Chilton-Colburn analogy. Does anybody remember? Chemical engineers, you should remember that. That is, the basis for that is in the underlying governing equations, which are the same for the three processes. Okay, any questions? Am I going fast, slow? Okay. It cannot be, I have to get you guys a bit more involved. You cannot be so quiet and laid back. Okay, this we already talked about in the last class, shear stress versus the shear rate. A Newtonian fluid has a linear straight relationship, and a pseudoplastic, which has a decreasing viscosity, shear thinning, and a dilatant fluid has an increasing viscosity, the drilling mud being an example. And also there is something called the Bingham plastic, which behaves like a Newtonian fluid once it starts moving, but it won't start moving until you apply a critical shear stress. Can anybody think of an example of that? Polyethylene would fall into this category because they start moving. As soon as you apply the shear stress, they start moving. So they do behave like a fluid. Here, what this shows, the Bingham plastic, is a type of material which will not move even if you apply a stress until that stress exceeds a critical value. And that critical value is this. And once you exceed the critical value, it will start flowing like a fluid, like a Newtonian fluid, for example. And certain materials, we would like it to have that property. Okay? Paint is a good example. So if I take a paint and apply it on the wall, if it keeps running, it's not going to be good for me, right? So when I apply it, it should stick to that. It's still a fluid, but it should stick there. What are the force that is pulling it down? Gravity, right? So it should have the ability to resist the gravitational force that makes it drip. That means you must have an yield stress. Okay, so you design your paints in such a way that they will have a small yield stress so that they don't flow right away. Okay, toothpaste is another good example that has that kind of a behavior. Okay, so when you apply a little bit of stress, it will start flowing, but if you throw the toothpaste on the wall, it's going to stick there for a while. Okay, so there are different kinds of materials in nature, and we need to be able to understand and describe them by mathematical models. So a bit more classification on non-Newtonian fluids. So there are some fluids that viscosity changes not with shear rate, as we saw in the previous example. Okay, in all these cases, as I increase the shear rate, the slope changes. When the slope changes, that means its viscosity changes. Okay? But there are some material that, even if you apply a constant shear rate, will become thinner with time, will start flowing easily with time. Okay, so those are called the time-dependent viscosity behavior, rheopactic and thixotropic. These are two opposite behaviors. One decreases, the other one increases. Apparent viscosity decreases, thixotropic, apparent viscosity increases. Okay, so there are some examples of lubricants and drilling mud, etc. Okay, and similarly, we have already seen the dilatant and the shear thinning. So they depend on the shear rate, not on time. You should go through these notes again because the quiz is going to be about describing these things. Okay, and then also onto the books as well. Okay, so the next property that we need to look at is something called the surface tension. Okay, when you have two fluids that are immiscible, gas liquid, vapor liquid. Okay, so what happens to the interface? Why is there a definite interface, even between oil and water, for example? Why don't they mix? Okay, you can understand the behavior again at the molecular level because all these macroscopic phenomena have a fundamental reason at the microscopic level, at the molecular level, the way that they interact. So if I have a liquid and a gas, a molecule that is at the interface is going to face different types of forces on both sides. What do we know about gases that is different from liquid? Density is much lower. What does that mean? The molecules are farther apart. There are fewer molecules in a given volume. Whereas in the liquid, they are closer together, they are packed together, they are a lot more, so their weight is higher, so their density is higher. Okay? That means the mean free path on the gas side is going to be larger than the mean free path on the liquid side. That means it's going to face a different interaction, maybe more attraction with the liquids than with the gas. So that surface will tend to curve, the interface will tend to curve. Okay? In fact, if there are no other forces, if you have a droplet of water in space, for example, it will assume a perfect spherical shape. Okay? Because that is the closest configuration where all the molecules, internal molecules, of course, will have the same experience, but at the interface, that object will give you the minimum energy, if you like. So there is another way of looking at this. This is a thermodynamic viewpoint, that will look at energy minimization to predict the shape of the interface. But we are in this course going to look at mostly forces because it is a dynamics course. Okay? And to capture this microscopic phenomena, we need another empirical equation, just like Hooke's law, Newton's law, and Fourier's law. And this is given by the so-called Young-Laplace equation. Okay? And what does it say? It simply says that the pressure difference, there is a pressure difference that exists across as you go across an interface. The pressure inside is higher than the pressure outside. Okay? That pressure difference is proportional to the curvature. Del dot n, here we are now introducing symbols, vector symbols. N is the normal, a vector that is normal to the surface, and the gradient operator is just a gradient operator. So a dot product, we will review these pretty soon, gives you a scalar number. It's a particular way of taking a product between two vectors. Okay? So this is a well-defined quantity, and it's a measure of the curvature of the surface. Okay? And the property that we are introducing here is called the surface tension. So you need to figure out the units for the surface tension in such a way that you make this equation consistent. Okay? So on the left-hand side, you have a pressure difference. It's not a pressure gradient, but a pressure difference. On the right-hand side, you have 1 over r. Okay, the radius of the curvature, which is 1 over r, 1 over the radius of curvature. That's an empirical equation, okay, that relates how the pressure jumps across a curved interface. And this has very important consequence in terms of bubble columns, where you're bubbling the air into a fermenter or a reactor. So this equation will appear as a boundary condition when you're studying fluid interfaces. Okay, so this is the scalar version. When you have a perfectly spherical object, there is only one radius of curvature. That is the simpler form of the Young-Laplace equation, which you may have seen earlier. But the vector form of it is given above, the more general one, for an arbitrarily curved surface. We'll come back and use these later on, but we are just introducing them right now, and introducing them as strictly definitions. Each one defines a new property. Okay? This one defines the surface tension. Previously we defined thermal conductivity, diffusivity, and viscosity. Here is a picture on the left side in a glass tumbler, a penny, I guess, that's floating. Does that surprise you? I guess you might have seen this, you might have done this experiment too in high school or something. Can you explain what is happening there? What do you think the density of a copper or material like that? Is it going to be lower or higher than water? Higher, right? So why does it float? It is on Earth, it's not in space. You can actually guess that too because the surface is flat. The liquid surface is flat. Right? How can you explain? That was actually, to simulate that is one of the doctoral theses of my most recent student who just graduated. He simulated how to predict the shapes in a general case. When you have bodies that are floating, what are the forces that can act on that are in equilibrium so that this shape is maintained, this status is maintained. So can you identify? This is the kind of thing, as a researcher, you should be able to do. When you see a curious thing like this, start thinking about it. What is happening there? Somebody start the discussion. What do you think happens? What goes through your mind when you see that? Good point. It could be. I could have deceived you, right? I could have put a very heavy material there. But let's talk about it. If it is glycerin or a very viscous material, but still the density of that copper is greater than the density of the glycerin, should it float? That's a good observation. It could be that, but we will rule that out. It's not that.
In water molecules close to the surface is higher than that. You also think the net force is that thing.
The net force? What do you mean by the net force? What are the forces? Identify the forces.
I mean,
Let me simplify the diagram. So if I look straight horizontally, okay, this is the kind of picture I will see. That's the coin. Oops. I'm getting into that situation again. Okay, let me go to the next one. That's the coin. And the interface, something like this. Okay. So that is the liquid. This is the liquid surface. You expect that. For example, if you do a capillary rise experiment, I take a fluid in here and I stick in a capillary. What do you expect? The liquid will rise, right? And it's not going to be straight. It's going to have a curvature, a meniscus that is curved like this, depending on whether it is wetting or non-wetting. It could be like this, or it could be like this, or whatever. Okay. So in which case it may actually be depressed. So the surface gets curved, and what we're talking about in the Young-Laplace equation is the forces due to curved interfaces, the forces at such curved interfaces, which is what the Young-Laplace equation describes. So as you said, there are differences in intermolecular interactions between the gas here, the liquid there, and the solid there. Gas or vapor. There is a three-phase contact line at this point. Okay, so there is a force that is acting in this direction. That is the capillary force. Okay, the surface tension force that is modeled by the Young-Laplace equation. What other forces are on that? Gravity, the weight of the material, m times g. So that's going to try to pull it down into the liquid, and it is such that the density of this is higher than the density of the fluid. Suppose the interface could also be like this. The other scenario that's possible. Again, it depends on the working. Oops. I don't know why it does that. Okay, suppose the interface is like this at the top end. Then are there any other forces that we need to worry about? The adhesive force is the kind of the surface forces that we're talking about. Okay, but you're talking about here. At this point of three-phase contact, there will always be a force. Okay, but because it is submerged in a liquid, there is one other force that is important. What is that? Buoyancy force. Okay, and we are going to see what buoyancy. You must have seen it before. We are going to rederive that equation. Okay, so it's an interplay between these three forces: buoyancy force, surface tension force, and gravity, the weight. Okay, but it is such that the capillary and buoyancy force combined outweigh the weight, so that it's able to support the weight. Okay, but if you disturb it slightly, such that you have an external force that momentarily makes the downward force bigger than the capillary force, then you can make it go, make it sink. Okay. So that capillary force plays many important roles, and this was studied by Lord Rayleigh in the 1800s or so. And one of the things that he studied was what would happen if you have a jet that you see on the right hand side, a water jet coming out of a pipe, and under certain conditions it will form these undulations, and then once the curvature comes in, surface tension forces take over, and this actually will break up into droplets. Okay, so the process of, even if you go home today and open the kitchen sink, observe what happens to the water that drips as you slowly decrease the flow rate. Okay, it will find a very nice jet, and as you decrease the flow rate, it will start breaking up into little droplets. Okay, what is the process that creates that? Again, capillary forces, the surface tension forces. If there are any slight undulations on the surface, then the curvature is there. The moment curvature is there, the surface tension forces act to collapse them into tiny droplets. Inkjet printers, for example, were designed based on this mechanism. This is called the Rayleigh instability, and we will see that later on. So I'm introducing the mechanisms that we can relate to in everyday life. Okay, now starts the real course. We have talked about general concepts so far. Now it's going to be all mathematics. Okay. Fluid statics. You have done fluid statics. What does it mean in your mind? Fluid is stationary, static. Okay. So what is the most fundamental equation that governs fluid statics? What do you know about static condition? For example, imagine the ocean to be almost static, right? As you go deeper and deeper into the ocean, what happens to the pressure? And higher and higher. Why does it happen?
Then the weight of
The weight of the fluid on top. Very simple to understand, right? So if you go at a certain level, there's a huge body of water above you, and gravity, the body force, acts over the entire volume. Okay? So the pressure at the surface plus whatever the weight of the fluid above that is going to give you the pressure at the bottom. So in any storage tanks, anywhere that you have, as you go down, the pressure goes up. And you know that equation as P equals rho GH. We're going to derive that. We're going to look at some of the properties of pressure. One of the properties of pressure is that it is isotropic. What does that mean? Same in all directions. Okay? So if I have a pressure at a particular point, it's going to be the same in every direction. Okay? So how do we show that? We show that by simply making a force balance. So in order to do that, I am taking a control volume. I'm doing this demonstration in 2 dimensions. Okay, so this is the x direction, and y direction is perpendicular to the board, and I have z direction in the top. And my g is going to be pointing downwards in the z direction, the negative z direction. Okay, g is a vector. Okay, so g is a vector. Will be 0 and minus gz. 9.81 in the negative z direction. So it's a vector containing 3 elements. Okay, so this is a demonstration that P1 equals P2 equals P3 in this case. These are labeled as, I think this is P1, this is P2, and that is P3. So I take under static conditions, so there is a fluid, this whole thing is filled with a fluid, and I take a control volume which is a triangle with an angle theta here. Okay, and delta x is the width in the horizontal direction, and delta z is the height in the vertical direction. So let me make a force balance in the x direction first. Okay, a force balance in the x direction. So what are the forces in the x direction? So if we go back to the figure, this process of writing balance equations, whether it is force balance, mass balance, or energy balance, it should become second nature to you by the end of this course. Given a control volume, understanding what the description is, writing the balance equation. Under static condition, what does it mean? There is no acceleration. So sum of the forces must be equal to 0. Under dynamic condition, that is not true. In the static condition, it is. So if I take this surface, this vertical surface, what is the force acting on that vertical surface? Now I'm going to consider a unit width perpendicular to that. Okay, so that is the surface. On that surface, I'm going to take a unit width. So the area is going to be dz times 1. Okay, of the red region that you have looked at here. That's the area. So what is the force? Pressure is force per unit area. So the force is going to be force in the x direction on this left surface is going to be simply P3 times dz times 1, right? Pressure times area. Area is dz times 1. Now, what is the component? What are the other forces in the x direction? Is there a component of force in the bottom surface in the x direction? No, because it is acting in the z direction. Okay? But on this surface, I will have a force that is acting both in the x direction z direction. So it is actually acting normal to the surface, meaning it is acting in this direction. Okay, so P1, so if I ask you to calculate what is the total force on the inclined surface, and that total force will be P1 times ds. What is ds? ds is this entire length. That is ds. Times 1, right? ds is the length perpendicular to the board, it's 1. So ds times 1 times P1 is the force. But I want to take the component of the force in the horizontal direction first, and then in the vertical direction. Okay? So let me do it like this. Theta, what can you say about that angle? Also theta. If that is theta, what is this one? 90 minus theta. Right? Because these two are perpendicular to each other. So these geometrical things you should be able to argue. Okay? And if that is 90 minus theta, what is this one?
Theta.
Theta. So what is the vertical component? P1 cos theta. What is the horizontal one? P1 sin theta. Okay. How many of you would feel comfortable if I give you a piece of paper and say go and write down that balance equation? You should be able to do that in this course. Okay. So having figured that out using just trigonometry, you just substitute. Okay. So it is P3 times z in the negative direction. That's why I have minus P3 dz. Remember, I wrote it down on this surface. It is P3 dz, but it is acting in the negative x direction. So I put a negative sign. And whereas this component is acting in the positive direction, right? But that is P1 sine theta times ds. Let me pause and ask the question. Anybody has a question on how I wrote that equation? This is the time to ask, because this is the time we need to calibrate whether I'm going fast or slow. And if you give me a blank face, I will have a difficult time meeting it up. Any questions? You don't want me to go into saying you, right? Are you guys okay? All right. Now, this is the force balance, and then I'm using the trigonometric relationship between dz and df from simply the triangle. Okay? So in this triangle, dz is this vertical line and ds is that inclined line. So the ratio of those two is equal to sine theta. Okay, so dz equals ds sine theta simply comes from trigonometric relationship. So I can substitute for that dz in here, and I will get ds sine theta, which is a common factor. So that is equal to 0. Why is it equal to 0? Because under static condition there is no force. If there is an imbalance of forces, then it will start moving. It will start accelerating. Okay, we are looking at statics, so the sum of the external forces must equal to 0 in each one of the three directions that we make. So this gives you then P1 equals to P3. That shows that the pressure is acting in all directions with the same magnitude. That is a proof in a sense of pressure is isotropic. Pressure acts at a point in all directions with the same magnitude, but if you identify a surface through that point, then you will realize that pressure perpendicular to that surface, whatever the orientation is. Okay? Any questions?
Why
Good. Please ask me that question. Okay? I'm happy because then I know that you don't understand something I can try to explain. If you're quiet, I have no clue. You just have to keep on piling more things, and then you say, "Oh, this course is too difficult." Too late by then. Okay. Why is dz equals ds sine theta? This is dz, this is dx, this is ds, this is theta. Right? And the triangle. So basically using triangles. Okay? So dx is going to be ds cos theta, dz is going to be ds sine theta. Okay? You should not be afraid to ask a question because you may think that it's stupid. There's no stupid question in this course. Okay, I need to gauge like whether you are absorbing it or not. So please do stop and what I do is I will explain these things and I will give you assigned work. For example, I'm not going to derive the Z force balance equation. It's exactly the same process, thought process. I want you to look at it. Okay? After the class, go and look at it and make sure that you understand. If you don't understand, next time come and ask me, because the very first part of the lectures would be, do you have any questions? That's your time to ask questions from the previous lecture. Okay? We are going through exactly the same logic. Okay? The only difference I will point out is when you go back to that triangle, there is a force that is acting in the bottom, upwards, in the positive Z direction, and there is a force that is acting, which is a component of the force that is acting on the inclined surface. Okay? And that's where you will get the cos theta from. But there is another force that is acting on that entire volume. What is that? The gravity, the weight of the fluid that is inside. So you need to find out what is the weight of the fluid that is inside, take the volume, multiplied by the density, gives you the mass, multiplied by g, that gives you the weight. Okay? And that is the only term that's extra in the vertical force balance equation. So this term, where do you think that 1/2 came from? That's the area of the triangle, right? Perpendicular to that, it's unit length. So you want to calculate the volume. The volume is the area of the triangle multiplied by the depth. But the area of the triangle is 1/2 dx dz. Okay, that's how you get the 1/2. And it is acting in the negative direction also. Okay, so the component of that force that is acting in the negative direction, this force is acting in the positive direction. So you should be able to identify every one of those signs, why it is. Okay? Yeah?
You had made it.
You mean three-dimensional? Or?
Like just as we see it on here.
Yeah.
And not.
Yeah, the reason I stretched it into the third dimension with the unit is I need to take the pressure and multiply it by the area. Okay, so I said let the area be defined with the unit depth. Okay, a more interesting variation on your question is, can you derive the same relationships if you have what do you call that? A pyramid shape. Okay, you can. The algebra gets much more complicated because you have complicated surfaces with difficult orientation. You need to resolve them. But the same result will apply for any arbitrary shape. If you want, I think I will give you this reference. It's probably in the list. Stephen Whittaker, Introduction to Fluid Mechanics. He has the proof of the same thing in a more elegant general setting. What he does is he takes x, y, z, and then he takes a triangular surface like this, and then takes the pressure acting on the triangular surface and shrinks that surface to 0 and shows that the pressure acting at that point, as you shrink that control volume, is the same in all the three directions. So that is a three-dimensional derivation. What we have done is a two-dimensional derivation with a pseudo third dimension just to indicate that it's an area. That's the only reason. It's a good question, okay? So that shows that you're thinking and you're following, okay? I need that. Okay. So pressure is isotropic. Okay, so far we know that under static condition, it acts in all directions with the same magnitude. The next thing that we are going to do, using the same logic, but using a different control volume. Okay, the control volume now is a cube that you see here with dx, dy, dz. Once again, g is acting downwards in the z direction. These are x and y. Okay, so when you write down the balance equation, the force balance equation in the x direction, you will get this equation. What do we mean by P subscript x? This is the pressure acting on a surface in the x plane. This is the pressure acting on a surface at x plus delta x plane, that is on the right hand side. This acts on a surface area dy dz, that also acts on the same surface area because of the geometry. But this acts in the negative direction, that acts in the positive direction. We sum them all up, under static condition it is 0. Okay. And then you take the limit dividing by delta y, delta z, delta x, and this is where, when we take the limit delta x going to 0, we want that to remain large compared to molecular dimension. We really don't mean a 0 point, but a point that has still a large collection of molecules, so that we can treat pressure as a meaningful variable. You do the same thing in the y direction, and you will get dp dy equal to 0. You do the same thing in the z direction, you will get dp dz equals minus rho g. Why? Because in the z direction you have three forces. In the x and y direction you basically have two forces on the two surfaces, like this and the other one. But in the z direction you have this force, the bottom force, and then the weight of the fluid in the control volume, which is rho times delta x, delta y, delta z, which is the mass multiplied by g. And that will give you this equation. We put all these three equations in a compact form as gradient of P equals minus rho g. Okay? That is the fundamental hydrostatic equation. And it is valid, in fact, even though we derived it in Cartesian frame, you can apply it in any reference frame, whether it is cylindrical, spherical coordinates, etc. Any questions on that?
So, an example too, we assume that there's a lot of pressure in the x direction, and the positive and negative, even though it's not shown in the problem statement.
Yeah. Okay. If you are taking a small control volume in a fluid, the pressure will be there in all directions, which is what we showed in the earlier one. Pressure is isotropic, so it will be acting in all directions. So it's not shown here, but there should be an arrow there, which indicates that there is a pressure on the. As I said, pressure at a point acts in all directions. So the moment you identify a surface through that point, you immediately know which direction the force must act due to pressure. It is in the normal direction. Okay. Any other question? Yeah.
In last case, in the triangle case,
Yeah.
as one shifts to 0, the gravity drops out. But while in this case, there's still a gravity.
Very good question. I guess I sidestepped that, right? You have to look at this equation. Okay, so as delta x, delta y, delta z shrink to 0, this term goes to 0, but these terms are not multiplied by x, delta y. Right? So that term doesn't go to 0, only the gravity term goes to 0. What it says is, as the volume shrinks to 0, the body force, the force that acts over the entire volume, goes to 0. So gravity is a force that acts on a volume, not on a surface. So when the volume shrinks to 0, the gravitational component of the force must go to 0. Because we need a certain volume, certain mass for gravity to act. And mathematically, you see that in this case, as delta z goes to 0, this term will drop out, but these are not multiplied by delta z, so they will not be equal to 0. Now, your question is, what happens in the second case? Okay, why do I have still? Because we are trying to prove two different things. In this case, we are trying to prove the isotropy. So we are shrinking the volume to 0 with the volume force going to 0 as we shrink it. Whereas in the second case, okay, you have delta x, delta y. Okay, and you're going to divide everything by delta x, delta y, delta z. Divide by delta x, delta y, delta z. So that cancels off. Okay, and on the left hand side, what you will have is Pz minus Pz plus delta z divided by delta z. The delta x and delta y will cancel out. Do you see that? It's a good question. It's an important thing to understand. Okay? Why did I not use the gravity term in this derivation? The reason is, this is the balance equation, okay, which we know why. There's pressure times area, here mass times the volume. Okay, I mean the volume times the density times G. And then I'm dividing everything by delta x, delta y, delta z. So here I lose all the term, I have only rho G. On the left hand side, I lose delta x, delta y. And I have delta z in the denominator. Then I apply the limit process. In the limit of delta z going to 0, what happens to this term? That term becomes dp dz. Okay? So here I'm actually deriving a force balance equation. In the previous case, I'm showing why the pressure is isotropic. Okay, any other questions? Yeah, here I have this TPS exercise, the first one. This is I want you to do from memory. The TPS exercise apparently works like this. I attended a teaching workshop a couple of summers ago, and that's where I learned about these techniques to get you guys active. Otherwise, you're just passive and doing nothing, right? So this is called think, pair, share. You think, and then you pair, and then you share your ideas. So I pose a problem, you think about it individually, you write out your answer on your piece of paper. And then two of you get together and exchange your ideas. Okay? So it helps in kind of identifying where in the thought process you could have problems. Okay, and then we will discuss that issue. Okay? So here I'm saying recall and state how you would determine the buoyant force of immersed objects using the basic hydrostatic equation, which is what we derived. Okay? Develop an expression for the buoyant force exerted by a fluid on an immersed cube of side A at a depth of h from the free surface. So the problem I'm posing to you is the following. This is the free surface, and I have a cube horizontally laid out with the surface, and it is at a depth of h from the free surface. I want you to calculate what is the buoyant force on that. And then the question is thinking, if the orientation of the cube is changed, will the buoyant force change? Does the buoyant force depend on the density of the solid? These are all the issues that we need to think about. I have about 15 minutes, maybe it's worth spending the time for you to get working on this, okay? So that is the situation. The cube side is A. Each side of the cube width or length is A, and it is at a distance h from the free surface. And the equation is gradient of P equals minus rho G, or I think I've given you the other one too, which is P equals P0 minus rho GZ. When you integrate that. And the pressure at this point, let's call that as P0. Let's take it as 0 to simplify it. So take about 5 to 7 minutes. See how far you can progress. Think through it. Write it down. And then carry on to exchange that. We'll go through the solution to the problem. Able to understand the question that I have posed? Any questions on that? Clarifications? Anybody get an answer to that? What is the expression for the buoyancy force? Okay, start sharing your ideas. Talking about it helps to get you there. So why don't you tell me together and just share what your thoughts are. Let's see what we can. What did I say? You two, and you two, and three of you, and two of you. It must be something boring. It must be something boring.
No. I want to learn
These are very basic
a new
things.
method to teach. And maybe I don't understand it very well. When I listen to it, I feel I understand it from a new point.
Okay.
I understand it better.
That's good. That's good.
And I can bring it to the listening function to
You can
the
listen to the recorded lecture. I mean, it's up to you. I mean, you want to come, you can come. But I'm just wondering, it may be too low level for you.
No. I like it. And I wondered, how can I download the stuff?
Oh, okay. I need to add you to the Moodle page. Then you'll be able to access. I'll do that tonight.
Okay.
I have your email ID. So
Yes. I think your tutorial is different from the teaching method in China.
I see. Okay, that's good then. That's new. Yeah. That, okay.